In this video, we're going to look at the example from pages 31 to 34 of the course notes, dealing with an example of how to use the parallel axis principle in order to find the second moment of area for an I-beam, and we'll be considering both the second moment of area about the x axis and the second moment of area about the y-axis. So what the parallel axis principle tells us is we're not dealing with a regular shape like a circle or a rectangle. We have to divide our section into shapes that we can manage. And so what we'll be doing here is dividing this shape up into three parts. We're going to have a rectangle here, red line here to separate it off, and that's, we'll call this shape number 1. We'll have this rectangle with this long thin one in the middle, that's rectangle 2, and it gives us a third rectangle at the bottom, that's shape number 3. And the course notes refers to these by the technical names 1 and 3, the flanges of the I-beam, 1's the top flange, 3's the bottom flange, and 2 is the web of the I-beam. So sometimes we'll refer to areas 1, 2, and 3, and sometimes we'll refer to them by the name for the part of the beam which it applies to. And the important part of the parallel axis principle is that we consider where the centroid of the shape, so for example, shape 1 is from the centroid of the I-beam as a whole. So that's an important measurement we have to consider. So let's have a look at, first of all, the second moment of area about the x-axis. So let's remind ourselves, this is when we're imagining we're dealing with a force being applied here. So it's been applied relative to this x-axis, which is running horizontally across our I-beam. So we want to deal with each of these rectangles. We're going to work out the second moment of area for them with reference to where they lie with regards to the centroid. So what the parallel axis principle tells us is that for every individual part of this, when we're dealing with rectangles, the contribution to the second moment of area of each section is going to be given by Ixx is equal to bd cubed over 12. That's our standard formula for second moment of area, but the x-axis for a rectangle. We're going to add onto this AC squared. Now, A is simply the cross section of each of our rectangles, which we'll take one at a time. The C squared is a difference between the distance between the centroid of the I-beam, that's that x axis, and the centroid of the rectangle we're looking at. So for each rectangle, we're going to indicate in the diagram where its own centroid is and work out that difference C. That's going to be something we're going to need in each case. So let's take a look at rectangle 1 first of all. So if we consider rectangle 1, we have a breadth of 100 millimeters and a depth of 20 millimeters. That we can take from the diagram. So our values for B and D are established, and our value for A is going to be 20 times 100, because the area of that section, which is 2000, should put units, millimeter squared in there. What is the value C? Well, let's take a look on our first diagram. The centroid for area 1 is going to run through the centre of it. And if it has a depth of 20, then that gap between the top surface and centroid is going to be 10 millimeters there. If we have a distance from the centroid to the top, I'll mark this in purple here, from X to the top of the beam of half of 300, that's 150. That means C is going to be equal to 150, the distance from the centroid to the top of our I-beam, minus 10, which is the distance from the top of the I-beam down to the centroid, that blue dotted line, across area 1. So our value for C is going to be 140 here. Now, it might be worth if this is not clear, pausing, going back and looking at how I've done this, because this is sometimes the thing which can be most confusing in the parallel axis type problem. But that's where we get, and I should have put in our millimeters there as well, and that's where we get all of our values from. So we have D here, B, A, and C. So we can now solve for rectangle 1. Ixx is going to be equal to 100 times 20 cubed divided by 12 plus the area, which is 2000 times 140, and again that's squared. So we can work this out. And you'll see in some, in fact it does it in the course notes in some cases, that they work out the BD cubed over 12 and put it in a column, and the AC squared and put it in another column. That you're very welcome to do that. There's absolutely no problem with laying out your answers like this. But once we know what we're doing, it just makes just as much sense to put our answers into one formula and then enter into our calculator. And when you put all of that into your calculator and you put it into scientific notation, the answer we get is going to be 39.27 times 10 to the 6 millimeters per 4. And you wouldn't be wrong here if you decided to write 3.972 times 10 to the 7 instead. The course notes sometimes likes to stick with powers of 6 or powers of 9 or powers of 3 because it makes for an easy comparison and easy addition between different second moments of area. There's absolutely no reason not to express it in whatever way makes sense to you, but the answer, whichever way you work it out, is going to be equal to 39.27 times 10 to the 6 millimeters to the power of 4. Now, it's relatively easy to establish that rectangle 3 is going to have the same second moment of area about the x-axis as rectangle 1. So I'm just going to write that down, but I will say a little bit about it before we move on. Just let's say rectangle 3, and its second moment of area for the x-axis of 39.27 times 10 to the 6 millimeters. Now why is this? Well, we can see immediately that the values for D and B are the same. It's a depth of 20 and a breadth of 100. Its area must also be the same because that's dependent on the depth and breadth. So the only other thing to consider is C the same? Well, if we look from our centroid down to the bottom of our I-beam, again we have 150, and if we come up halfway across the depths of rectangle 3, again we can see coming up 10 millimeters here, and so the gap, I'll mark this in red to make it really clear as 10, the gap in the centroids must be 150 minus 10, so we're left with 140. So same value for D, same value for B, same value for A, same value for C. So rectangles 1 and 3 must have the same second motive area. And in an assessment question, and we'll often deal with I-beams, it is completely acceptable to write that rectangles 1 and 3, or top flange and bottom flange, however you want to express it, have the same second moment of area. And there's no need for any further calculation. You can just write down they have the same value. There's no extra marks to be gained for saying otherwise. And so we've worked out 2 of our 3 rectangles. Well, the good bit comes now, and by that I mean just raise this and tidy it up again. So I'll mark back on our 3 areas. We've dealt with 1, we've dealt with 3, so it just remains the web. Rectangle 2 we have to deal with. So I'll write down rectangle 2 here. I'll draw a rectangle 2, this long, thin rectangle. So let's go on up here and have a look at what we know about this. Well, we know the width of the breadth, I should say, of the rectangle is 10. That's given in the question. That's what that means. So what is the height of the rectangle? What is this distance between the flanges? Well, the total distance we're told is 300. and the depth of each flange is 20. So this blue line here, the height, the depth of rectangle 2 must be 300 minus 20 minus 20. If the whole thing's 300 and there's two 20s at either end, that leaves us 260 millimeters, and that's the value, you should say, for D, for rectangle 2. So we can mark this in our little diagram we're making here. We're told breadth is 10, depth is 260. Now, we can work out the area from that. But before we start to work out the area, let's think about what the value for C is here. Well, looking at this rectangle, its centroid, which I'm marking green here, is the same as the centroid of the I-beam as a whole. And the centroids are the same. It means there's no distance between them. So the value for C is 0. So when you have part of your I-beam, which the centroid for the whole I-beam runs through, it simply has a second moment of area found by Ixx equal to BD cubed over 12. We don't need to consider this plus AC. In fact, if I wrote it in here, plus AC squared. Okay, we can work out A, but C is going to be 0. And anything multiplied by 0 is 0. So for the middle section, it's just a standard rectangle problem. We have our values, missed it, a 0 in that 2. We have our values for B and D, so we can write this in. 10 times 260 cubed divided by 12. And again, if we put this into our calculators, and if we change it into scientific notation times 10 to the 6, we're going to get 14.65 times 10 to the 6 millimeters per 4. So that's how we find the individual second moments of area about the x-axis. The final thing to do in this question is to say for the I-beam, Ixx is going to be equal to the sum of the three rectangles. So we'll have the Ixx for rectangle 1, for rectangle 2, and for rectangle 3. And I'll show you the nice table that they use in the course notes, but there's really, as I said, you can just stick them in as I'm about to do. So what they do in the course notes, they lay out this nice table here. So they work out the BD cubed over 12, and they work out the AC squared separately, and they add them together in this column at the end here. That's just what we've done straight away. And so you can see 3 values, and then they've got a sum total at the bottom. So that's what we are effectively doing here. We know that area 1 is 39.27 times 10 to the 6. Area 2 just worked out is 14.65 times 10 to the 6. And the area 3 is the same as area 1, 39.27 times 10 to the 6. And here we have 93.19 times 10 to the 6 millimeters to the power 4. And just something to observe very briefly here, but look at the contributions that areas 1 and 3 make. Each one is more than double the middle rectangular section. And so you can see the advantage in the I-beam. This is part of why this shape has been selected in engineering, because it's going to add greater second moment of area without necessarily adding a great deal more material. And if you considered a rectangle with the same total cross section, you could very easily make a comparison. So that's just a little aside there. But of course, the example also goes on to get us to look at the second moment of area about the y-axis, and so I'll do that as well. I'll copy our diagram across. So again, let's remind ourselves when we're considering the second moment of area about the y-axis, what we're considering is if a load is being applied like this across our beam here, so perpendicular to that axis. Now, we already know to expect from the course that we should have a lower second moment of area for this particular beam about the y-axis, but let's continue with the example and let's prove this to ourselves. this is the case. Once again, we'll divide our beam into 3 sections because we know how to deal with rectangles, we don't know how to deal with eye shapes. So we'll separate them here, here. So 1, 2, and 3, just as before. And again, we want to consider each rectangle, the 2 flanges in the web, to work out what their second moment of areas are going to be, because the overall second moment area is going to be the sum of these 3. But something to observe before we begin, our centroid is now this line here, this purple dashed line I'm putting through. But hopefully you can see the centroid of each shape, the centre of mass, centre of area of each shape is going to be the same as the y-y axis. And that means that in every single consideration here, we're going to have no value for c. C is going to be 0 in every case. So that means that in every single case, we can exclude this AC squared term and just go with the formula for the rectangle. So it's just adding up 3 rectangles because they all share the same centroid, the same y-y axis. So we'll take these in turn, but we're not expecting too much from this. I'll diverge slightly from the notation in the course notes, but I'll explain what I'm doing as I do it. But let's consider rectangle 1. And we know from the first example that I can actually say rectangle 1, I put in brackets, and 3. Both of these will have the same value because they're both the same shape with the same dimensions. And if it mattered, the same distance from the XX axis, which it doesn't in this calculation. So let's have a look. These rectangles here are shaped like this, as we drew before, and the dimensions are 100 by 20. Now, where I'm diverging from the course notes is that the course notes continues to use BD cubed over 12, but they now call what we were calling the breadth before the depth, and the depth, they call it the breadth, and I think that's slightly confusing, so I'm going to stick with the definition we used earlier in the notes. But the most important thing is you get things the right way around, and the right way around means the thing that we are cubing is this dimension here when we're dealing with the y axis. So we are still going to call this our value for B and this our value for D, except now our formula is what we introduced earlier. IYY is equal to DB cubed. So if you remember, I should say over 12. If you remember that for the XX, it was BD cubed. Well, we've got the same B and D, but now it's DB cubed over 12. And so it's going to be different for this rectangle. And we put it in here. And what we're going to have is 20 times 100 cubed over 12, giving us an answer of 1.67 times 10 to the 6 millimeters to the power 4. And this is perhaps where you can see why in the example they've chosen to keep everything to the power times 10 to the 6, because this one will only be 1 point something, and it makes it all easy to compare. But again, like I said in the previous question, if you did things in proper scientific notation, there's absolutely no reason not to do that, and it's whatever makes sense for you, because this is purely a choice made by the example. So that's look at 2 of our 3 second moment of areas, because rectangles 1 and 3 have been dealt with. So let's look at rectangle 2 now. So rectangle 2, we've already worked out the dimensions of rectangle 2 because we did that in the first part of this example, but I'll write it in again. The breadth of 10, a depth of 260, and again I'll use the formula for a rectangle for the second moment of area about the y-axis, and that's db cubed divided by 12. And so 260 times 10 cubed divided by 12. And if we put in our We put in our calculations now. What we get as an answer for this is something that's actually very small in comparison. And again, not the way you normally express things in scientific notation unless you're deliberately trying to keep everything the same power, which is what we're doing here. So this is 0.02 times 10 to the 6 millimeters to the power 4. But let's give this a little bit of context here to see what you'd actually be dealing with in your calculator, because I sometimes think those examples do all work out quite nicely. They're always not very clear. So this answer on the calculator, I'll just write it here, would be 221,666, then 6 recurring after that. So we would normally be writing 2.17 times 10 to the 4 here, but because they are trying to keep everything comparable in times 10 to the 6, that's why it's expressed like this. So I wouldn't worry in particular. If you gave me an answer like this, or you said 2.17 times 10 to the 4, all perfectly acceptable. In the end, we're going to stick it all into the calculator and add them all together, so it's not something to be overly concerned about. But I'm trying to make this video consistent with what you're looking at in the course notes. And so again, we can add our 3 rectangles together to get the second of the I-beam. It's about the y-axis. So let's add up our values, and we've got 1.67 times 10 to the 6, and because we've got 2 of them, we might just as well write it as in brackets times 2. Then adding on 0.02 times 10 to the 6, the value we obtained just there for the second rectangle. And adding the 3 of these together, we get 3.36 times 10 to the 6 millimeters to the power 4. And again, the course notes has a nice little table, but of course, I'll show you just to conclude. But of course, in the table, all of the values in their AC square column are 0, because remember, if we look at our shape here, there's no distance between this vertical axis and the vertical axes of each of the shapes, because they all are lined up. What I mean is, this is the centroid of the flanges, this is the centroid of the web, and there's no way of measuring a distance between that because it's the same line, it runs along the same line. So that gives us the answer for the second motor variable, the y-axis. And if we compare these two values, we can see it was 93.19 times 10 to the 6 versus 3.36 times 10 to the 6. So significantly bigger, in fact, something in the order of 30 times bigger. So it really does, again, illustrate that the direction in which we support a load with a beam, so how the beam is orientated, is going to make a big difference in terms of the second moment of area. And that takes us through the examples on pages 31 to 34. And this is the same method that you'll use in the tutorial questions that follow on from this.